Thanks. I would like to thank the organizers for the opportunity. So I'm going to talk about fractional Wannier orbitals and tight binding gauge fields in Kitaev model with flat band Majorana bands. So here is an overview of my talk. So I'll be talking about first construction of low energy tight binding models for the fractional particles in the background of gauge fields, and then I'll discuss flat bands and Wannier orbitals and fractional Chandni insulator phases for Majorana fermions. This is based on this reference done with Professor Bhaskaran and Tanmay Das. To give a context of the problem, let's consider the antiferromagnetic Heisenberg model. For two sides, the ground state will be simply the nil state, up-down state. Let's say, but when you have frustration in the model, so we can have all kind of spin configurations allowed in the state. But at low energy, only singlets will contribute. The triplets will have high energy states. So to get the low energy physics, we have to impose a constraint on the allowed Hilbert space. So that will generally give rise to gauge fields. So the gauge fields will emerge in the low energy physics. And the single spin flip excitations will give rise to high energy modes. But when you apply some external fields or something like that, and then couple these gauge fields and the matter fields, so the interesting physics arise. So one such example was done in this work, where we found some kind of a glassiness in the Kitaev model without having to do with any disorder present in the model. So that is mainly due to restricted dynamics of the excitations. Here the excitations have fractional statistics. So that is the main reason for the glassiness present in this model. So mainly the gauge sectors, different gauge sectors will give a platform to manipulate these fractional particles. So that is what my main goal is to do here. So in this talk I'll discuss the low energy effective tight binding model to these fractional particles, mainly keeping them in mind that like there is a flux in the background, so I have to keep that in mind, and then I have to satisfy the constraint which is present in the background in constructing the low energy theory. So this I'm going to do it in Kitaev model. Kitaev model is originally written in spins. So, but if you take Majorana representation for the spins, this will simply look like this, where the C operators are the Majorana operators, and U operators are gauge operators, which are Z2 operators, which takes +1 and -1, which leaves on the bonds between site I and J. So if you take all the products in the given plug weight, 6 U operators in the plug weight, it will measure the flux passing through the plug weight. So if you take this multiplication to be +1, it gives rise to 0 flux, and if it is -1, it gives rise to pi flux. So just by arranging these fluxes in a given manner, we can tune the Majorana dispersions and all. So here I am taking one such example denoted by 2x2 configuration, where 2 is the distance between these pi fluxes. Just by taking this kind of a configuration and fixing these U operators, this will simply look like a Majorana hopping in the background of some superlattice. So this will right away give the band structures and all. So here is the band structure. This is for the next nearest neighbor hopping k equal to 0. This is for k not equal to 0 case. So as you can see, these bands are very nearly flat. By tuning k, you can tune the bandwidth and the gap between these bands, low energy bands. So by changing the distance between the flux also, one can tune this bandwidth. So you can make them even more flatter and flatter. So here my goal is to construct a low energy theory for these bands which are close to the zero energy. So the way to do is that this is a general procedure. I may not need this much thing for the Majorana construction and all. So the general procedure is to take the original Hamiltonian and construct a self-consistent super exchange kind of a potential H prime, and then project out to give rise to the effective Hamiltonian. Let's say if I'm considering p bands in the conduction band and p bands in the valence band. In this model, we have particle hole symmetry, so they have equivalent number. So if I just to take this whole Hamiltonian, the way to do self-consistency is to write the general hopping kind of Hamiltonian in the momentum space, and then fit this hopping terms with the general band structure. So here the hopping parameters, I mean the real part and imaginary part make direct connections to the metric and gauge freedom in the problem actually. So by fixing this imaginary part in such a way that it gives rise to the flux present in the model, one can fix these hopping parameters, and then we can study further the effective Hamiltonian. So I will give you an example where let's say I am considering here 4 by 4 flux configuration for the Majorana. So the first step is to construct the Wannier orbitals for these Majorana fermions, and then I can fit the hopping Hamiltonians, keeping that in the given unit cell there is one pi flux residing in the unit cell. So I have to keep that in mind and then fit the band structure accordingly, and then I'll get the effective band Hamiltonian. So here there is a catch for this Majorana fermions to do Wannierization. Here we have to impose particle hole symmetry in every process, like in constructing the trial wave functions and in taking the unitary matrices also. So the Majorana orbitals here are like a superposition of the electron hole orbitals in some sense. So I have to always consider the particle hole symmetric bands here. So this is how it is done. So, and then let's say after I get the effective Hamiltonian, I can construct all the invariants of the bands. So here I am plotting the quantum metric and Berry curvature are the invariants here. If I can write some scalar invariants out of these metric and Berry curvature, from Berry curvature I can point out chain number, and from quantum metric I can write some invariant quantity G. Here I am plotting those quantity for comparing with the pi flux, 4 by 4 flux case and the 0 flux case, and there is a huge change in the in these quantities, and there is a interesting phase transition here that I am not going to talk about. So interestingly, these bands satisfy the conditions to be an ideal chain insulators. Those are these uniform Berry curvature and this trace condition where trace of a quantum metric is approximately equal to Berry curvature at each k point. So these are the kind of ideal conditions for the chain insulators. As you can see here, I am changing for different k values. I am plotting the Berry curvature and the difference between these two quantities. So as you can see, for the higher k values, we have a very uniformly distributed quantities. So at these scales, so if I take any interactions among the Majorana fermions, I can get fractional chain insulators. So these are discussed in these kind of these references. So now I'm going to discuss gauge invariant mean field theory to study the fractional chain insulator phase for this. I mean, there are many numerical calculations to understand the fractional chain insulators. I think we wanted to try analytically with a minimal model. So I took the effective model and then took some interaction Hamiltonian, where these are all 4 in number. These are all Majorana fermions in the effective model, and these are the gauge fluxes residing in the 3 nearest neighbors between these 4 Majorana fermions. Like these are the 3 nearest neighbors of the honeycomb lattice. So by here I am considering some mean field parameters. So this is not sigma 1, this is sigma 2. So I am considering two mean field parameters where these mean field parameters are also kind of not, they are dictated by the gauge fields. I cannot take simply anything I want. So I have to follow these gauge rules where uh, I have to take care of the gauge freedom residing in these two bonds. So here I am forming, here is a mean field Hamiltonian where this effective Hamiltonian is 2 by 2 Hamiltonian, and then I am taking some general mean field terms with some density kind of order in this case, where Q is I've taken to be G2 by 2. So here effectively there are two bands in the original model. So I'm by doing this I'm getting four bands in this case. So the distribution of the orbitals in the two bands is getting redistributed into four bands. So if you calculate each band Chern number, they will comes out to be fractional in this case. So here this fraction can be anything, but by keeping stable mean field parameters, one can get the discrete kind of a fractional Chern numbers. So this we are going to do further and all. So if you have any doubts, you can check this reference. So to conclude, I have discussed how to constructing topologically non-trivial flat bands for the Majorana fermions and the Wannier orbitals and tight binding effective models for the fractional Majorana particles. Then I discussed the fractional chain insulator phase for the Majorana fermions using some mean field theory. So that's all. Thanks.
Questions?
If your system exhibits this fractional Chern insulator of Majorana fermions, is it going to have a thermal transport signature? Or how do you observe it experimentally?
I mean, here, let's say, here by applying mean field theory, we are just folding the bands and then gapping them out. So we have to tune the density of Majorana. I mean, we can do it by forming a complex fermionic thing and then tune the Majorana density and then keeping at the low energy band. Then one can get the fractional Chern number.
I'm asking about the signature. So let's suppose that you've got in a system, you're lucky to get a magnetic system which realizes this. And what experimental signature would there be of the fractional Chern insulator?
I mean, one can have gapless modes carrying the fractional charge. I mean, that's the kind of.
Yeah, so I guess what is that? So how would you see the fractional charge? I mean, in the non-interacting case, you would have this quantized thermal transport. But when you add the interactions in, I guess I'm asking, so how would that change?
I mean,
how do you see the interaction
so
effects?
what I'm saying is related to fractional quantum Hall kind of a physics, where one can see the edges, different kind of edges, which can give a fractional.
You have charge in that case. It's a little bit easier.
Yeah, here I don't know. Like maybe one can calculate with a thermal Hall kind of a.
Okay, thank you.
Yeah.
Any other question? Okay, if not, let's thank Yogendra. So that's the end of the session. We'll break for lunch.